Hey everybody, my name is Drew Turner. I'm the Director of Sector Coupling Solutions for Danfoss. I've been with the company now for about 10 and a half years, going on 11 years. I was in the industry with a global OEM for 17 years before that. As you could probably guess by my accent, I'm not from over here, but I relocated about a year and a half ago to Denmark because January was the perfect time to move to Denmark. But what I do, what our team does, is large-scale integrated energy system designs. And so a lot of what I'm going to talk about kind of plays off of what you heard from Kim and from Tuncha, both as far as integrated energy system designs and the opportunity for recovering heat from specific applications to electrify heating. That's what sector coupling is. So the opportunity with sector coupling is really, it's tying together two or more supply and demand energy systems is what sector coupling is. And so the biggest opportunity for a company like Danfoss is to electrify heating based on the heat recovery from cooling processes or just heat rejection processes. So that's what our team does, is work on those types of systems, basically tie cooling systems and heating systems together, whether it's a small scale industrial application or a large scale district energy recovering heat from a data center, for example, in Finland that we just worked on. But how to segment, simplify those complex system designs is really a critical aspect, is one of the learnings. I'm going to be going over the learnings that we've had from the projects that we worked on and the system designs of them. How source to demand differential is really critical. So Tuja kind of touched on this, and so did Kim. But basically, the difference between a heating system of the past and a heating system of the future is a boiler didn't care how much lift you were producing. You know, if you're burning something, if you're converting energy, and when you convert that energy, whether you're producing 180 degrees C or 130 degrees C, it's basically the same efficiency. That completely changes when you talk about electrification and heat pumps. So the work that you have to do becomes absolutely critical to not only the decarbonization potential based on the electricity usage, but also the payback. We're all, I believe, in this room significantly focused on decarbonization with electrification. That's why you're interested in this. But ultimately, the projects that you work on, it's amazing how fast projects move forward if they also have less than a 3-year payback, as opposed to a significantly longer one. And the differential that the work that you have to do from the cooling side to the heating side becomes absolutely critical to that. And I'm going to provide some specific examples and then go through the conclusions. Anytime you talk about electrification and heating and heat pumps, the first thing you have to do is baseline the conversation. When somebody says it doesn't make any sense to use hydrogen directly for heating and the electrification of heating and decarbonization, your correct response is, okay, but what are you comparing it to? You're probably right, but what are you comparing it to? So you have to start with the baseline. The baseline is a condensing boiler. In most cases, that's what you're replacing, as a boiler or a furnace and a condensing boiler specifically for this example. But all of those systems are operating on average from 0.85 to 0.95 COP. That's your baseline. Then you go to the baseline of electrification. What are you comparing to? Your baseline with electrification with heat pumps is an air-to-water heat pump, because in most cases, that's going to be the baseline efficiency at about a 2.5 to a 3.5 COP. And depending on how much you're boosting with the recovered energy to supply the electrified heating system, that's going to govern how much over that you can get to. But even with that baseline, you're still talking about a 35% operating cost, and this is highly dependent, 35% operating cost reduction and a 60% emissions reduction for replacing that condensing boiler with an air-to-water heat pump and using, and Kim touched on this as well, a grid that is 100% supplied by fossil fuel sources, so a combined cycle natural gas plant. If you do the math on that, you're still significantly decarbonizing because of that baseline that you're comparing to, and significantly less efficient with converting energy. But the other critical factor that comes into play when you electrify, when you combine systems together, and Kim kind of touched on this as well, is that if you're electrifying and you're using electricity, you're significantly at the mercy of that electricity. So ultimately what you're trying to do is tie to the grid to electrify and decarbonize, but that depends on replacing the fossil fuel sources that combined cycle natural gas plant, supplying that grid. So if you want to go beyond that 60% emissions reduction, it depends on replacing that with wind and with solar, but then you're at the mercy of the availability of those. So what becomes really critical is storage, and storage takes many forms. It takes the form of batteries, it takes the form of pumped hydro, it takes the form of thermal. One of the points that we make when you combine systems together is that the scale that you get to by just combining those systems together has a built-in storage factor that helps alleviate that supply-demand disconnect and that real-time price fluctuation that you see with electricity. So you can downplay the use of electrical energy at certain times when you have that electricity peak just based on the thermal flywheel of that larger scale energy system that you just created by combining systems together. But the opportunity, and again, starting with a baseline, the opportunity for recovering heat from cooling or just heat rejection is significant. And there's various forms of this. I'm a nerd to Sankey diagrams, if you will. This is a Sankey diagram showing from primary energy generation to primary or secondary energy use, how much heat or how much energy is just being rejected today with those primary energy systems. That's what we're trying to address with sector coupling, and that's what everybody who does sector coupling projects, combining energy system together, is really trying to address is this right here. The amount of rejected energy, which is about 2/3. Every Sankey diagram, there's so many forms of this, but every one says roughly the same thing. About 2/3 of primary energy is being rejected today. So that's the opportunity. Then when you start to combine energy systems together, the other thing that you try to do is simplify a very complex system. And what we learned from all of these projects that we've worked on is that you can simplify that by segmenting, making them work streams or swim lanes, if you will. Basically saying that you have a source, you have a boost, and you have a demand. If you segment it that way, then you simplify the process, and you can also interchange the systems that you design to, based on that source to demand, interchange those systems to fit together. And you can learn a lot by simplifying those. And ultimately, and this is where this is going, we believe, packaging those together into modular interchangeable solutions. That's what we're working on today. But if you segment it, you have the source, you have the heat pump, and you have the demand. And ultimately, this is a literal project that we're working on right now that's recovering subway heat to supply through a heat pump to electrify the heating system of a district energy system. That's how you segment this. And then you start to play with the system designs to fit with these and make sure that you have the solutions or can modify an existing solution to fit with that system design. But what, again, becomes really critical is limiting the overall differential or work that the heat pump has to do. Who's familiar with the term spark spread? Quick show of hands. Who knows the term spark spread? Anybody? Okay, spark spread is a critical term, and it's also called energy cost ratio. That governs the payback associated with a heat pump project. Spark spread in certain markets, Germany is actually a pretty good example. It's getting better here. But the spark spread is the ratio of a cost of a kWh of electricity versus getting that same kWh from gas. It's always more with electricity. And that ratio is ultimately critical to an electrified energy system, because if you don't exceed that ratio, what do you not have? Anybody want to say it? You don't have a payback. You have no payback. So if your spark spread ratio is 2.5, if your efficiency of your heat pump system is not 2.5, then you have no payback, or greater than 2.5, you have no payback. The magnitude of that difference governs the payback period. And ultimately, again, the decarbonization potential, because you use less electrical energy as a result of that, right? If you exceed that. But this is just showing, and I apologize, this is very busy, but this is decreasing efficiency with increasing differential. And it's summarized over here. What you learn is that for every 1K differential decrease of the work that a heat pump has to do, you're going to gain about, and this is universal, independent of the technology that's utilized, it's about 2% on the efficiency of the heat pump system that's applied to generate that heat, to electrify that heating system. That decreases the payback 2%, but it also critically decreases the electrical load, right? So it's not only about efficiency, it's also about electrical load, and also the blowback that we're getting on electrifying basically everything today. That blowback is significantly because we're making efficiency trade-offs on how we're implementing these electrified energy systems. Like if you can implement a significantly, 3 times the efficiency of the baseline energy system, you're using a third less power on average. And that is significant to the electrical load that you're adding to the grid. This is a summary of the projects that we've worked on based on the heat source. So again, segmenting based on source, heat pump, demand. This is the summary of the projects that we've worked on. And a quick summary of some of our learnings on this. The way we see it, especially if you're going to focus on district energy system, critical facilities, whether it's a data center, an industrial process, a hospital, anything that has a backup power system is going to be the future baseload energy source for a decarbonized electrified energy system. That is not only because of the high cooling temperature that you have with those systems and therefore less differential, it's also because you have an extremely resilient system. If it's a critical facility, that word critical becomes critical, right? Because you have a backup power system. And so that not only means that you have an extremely resilient cooling system for that critical facility, it also means that whoever uses that energy downstream as versus heat rejection is also going to have a significantly more resilient system because they're using that same energy that has backup power to it. This is the box plot of those same applications. What this is showing is the source temperature and variation. So if you're familiar with box plots, you have an average and you have a range. And this shows the average and range of the temperatures of the different applications that we've worked on. And you can simplify this and summarize it and it basically tells you, what do you focus on? If you're going to electrify an energy system, if you have choices, and that is critical, it depends on the choices that you have based on what's around you on how you can electrify a heating system. But if you have choices, what you want to try to use is those highest temperature sources, because that's going to guarantee that you're doing the least amount of work with that heat pump that's in between. And this is summarizing. You can also play with the system design, because what else do you know if I come from the cooling world. I spent 17 years working on product planning for chillers and air handlers and stuff like that. But when I started doing this, integrated energy system designs, one of the things that we recognized very quickly is that if you're going to electrify heating systems, heating has a dynamic that becomes really critical to how you want to design a system. And what chiller guys have been doing for years, for 25 plus years, and this was our centrifugal guys 25 years ago who came up with this, is designing series counterflow systems, which basically says you reverse the flow of a two-circuit system to match the lowest temperature cooling with the lowest temperature heat rejection and the highest temperature cooling with the highest temperature heat rejection. And what you do if you do that and you divide it up into two circuits, if you have a single circuit system, you have to do this amount of work with that single circuit system. If you have two circuits, you're dividing that up. And that higher differential within the heating system itself, and this is a literal example of our own data center on our headquarters in Norbor, where they have 43 degrees C heating return, and 67 degrees C heating supply. That high differential within the heating system itself, not from the cooling to the heating, but within the heating system itself, creates the benefit of the opportunity to divide this up into two circuits and divide up that work. And basically what you're doing is lowering down the overall work that the system has to do. In this case, and we modeled it to say if we had made this a single circuit system, ultimately we applied a two-circuit series counterflow system, the benefit was almost 20%. So it's significant just to play with the system design. This is a summary of the overall sources and the heat pump in between and the technology that you utilize or that we've utilized and the demand side. And again, segmenting it into the low temp, medium temp, and high temp sources, the different technology choices that you have in between, and the demand side. And I've got I know I'm running short on time, so I got to hurry through this. But this is everything that I've shown previously or that I'm going to show subsequently. What you're ultimately trying to do, again, is limit the overall differential work that you have to do from here to here. And so how you do that is, again, utilizing the maximum temperature source and ultimately doing the work to lower the temperature demand on the heating system side. And these are those examples. And I'll be going through a few of them. But this is an example. The other thing that we've learned is that if you're going to tie energy systems together, how you do it with the system architecture becomes really critical. And what the great news is, you can complicate you can simplify very complex systems by creating a system architecture that facilitates the business model of two completely separate customers. So a wastewater facility is a critical facility. They have a backup power system. The only thing they're worried about is maintaining their operation. So they don't want a heat pump in general on site that could potentially interrupt the operation of their wastewater treatment system. So you give them a heat exchanger instead, and then pipe that to a heat pump that's downstream of that, then build in the storage that Kim was also highlighting to, just in case you have a supply-demand disconnect, also based on the power that's available and the price of that power going into the heat pump, to then supply to the district energy system. And then you start to play with it and you say, okay, well, what are the other applications that we can, and this is a literal example as well, that we can work on. We just worked on one of these, worked on a few of them in Scandinavia and here in Germany. But what do we know about data centers? Data centers don't want to be in the heating business, right? But they've been thinking about this heat recovery opportunity all wrong. And so we started what we call the Net Zero Innovation Hub, which you may have heard of, which has several members, both data center companies as well as solution providers. And what we do is we're simplifying the process of designing these systems, basically saying, what if you have a heat reuse enabled data center, and we see this as the future of data center system designs, whether it's regulated, which it is now here in Germany, or if it's not regulated, for example, in the US, every data center we see moving in the direction of this. Don't give them something that penalizes their PUE, because in perpetuity, data centers are going to be focused on power usage, efficiency, or effectiveness, right? And so you don't give them a heat pump, you give them a heat recovery device that gives them free cooling and removes barriers to building new data centers. So you simplify a complex business model question of how do you enable heat recovery from a data center without penalizing their existing business model. This is how you do it. Give them a heat recovery station instead of a heat pump. And then you pipe that to the heat pump that ultimately boosts up the heat to supply to the district energy system. This is our own data center. The other thing that we point out is, if you want a soundbite, the only enemy of integrated energy system designs is DX systems, or direct expansion systems. If it's hydronic, then we know going into it, if it's hydronic on the heating side and hydronic on the cooling side, we know we can create a system ultimately that's going to have less than a 5-year payback, more likely less than a 3-year payback. If it's hydronic, it's relatively easy. It just becomes a question of how do you implement it. If it's not, then it's much more complicated. So what we look for is first hydronic. But this is our own data center heat recovery system. The other thing that we talk about is if it is a hydronic system, it's really easy to tie in to do heat recovery. Because this is the system that was implemented 3 years ago or 4 years ago. And then 2 years ago, implemented this. Basically what you're doing is adding a heat recovery heat pump to that existing system to preload the cooling of this same data center cooling system based on the demand on the heating side to supply the heat to district energy. And then what you're doing is just relegating the existing chillers to a backup system. Every data center loves backup. So you're adding to their backup system. A few more examples. Ultimately, what you're trying to do, again, is decrease differential from the source to the demand. The ultimate is an inverted situation, right? Because then you have an extremely efficient system. If you have for example, data centers, what's happening with data centers? AI, right? What does AI mean? More dense power generation or heat generation. Therefore, everything is moving to liquid cooling. Anecdotally, I heard last year, at the beginning of the year, 5% of data centers were being built with liquid cooling. At the end of the year, it was 20%. Now, there's some dispute over those numbers, but the point is there was an inflection point of last year being a transition to liquid cooling of data centers, to where that is becoming the most prevalent solution in the future. And that, in turn, means higher cooling temperatures. That means less work that you have to do to supply a heating system. ultimately providing examples such as this, where if you're going to recover the heat to a greenhouse, where you're heating the air to the optimal growing temperature of those plants, you can do it without a heat pump. It's a true symbiosis system, as we call it, just with a heat recovery station in between and no heat pump. A little bit similar to the data center or the previous data center, but using those same temperatures, supplying to a heat a brewery. The other discovery that we've had, everybody focuses on district energy systems first, on heat recovery and sector coupling. What we figured out is if you're going to really take sector coupling to its opportunity scale, then you need to focus on other applications, industrial applications, and enabling the business model of data centers to be located where those heat reuse customers are. And that's what we're working on now. And this is an example of that. So if you can recover heat to electrify a brewery's system, heating system, based on heat recovery from a data center, it's going to be about 3 times the efficiency of that same brewery using an air-to-water heat pump as an alternative. And so that is a significant opportunity, enough so that they will pay the data centers to co-locate on their site. That's the future sector coupling business model that we see form. These are a couple other examples, but I'm done on time, and I think I'm standing between everybody and drinks, so I'm going to shut up now. If you're interested in talking about any of these other examples that I'm very quickly going to slide through, then I would be more than happy to do it. This one is a more recent ultimate example. So aquathermal, you remember that geothermal systems, or a lot of what we've worked on? Again, what we're trying to do, especially when there's a coincident cooling and heating demand, that you're trying to meet both of them with a more efficient system, not only the heating and the electrification of that, but also the cooling. And aquathermal energy storage, or AEDIS geothermal system, is a really good solution for that. But the other thing that you'll notice here is if you're going to supply a multifamily system, then you don't want to boost the problem with heating systems of the past, another soundbite, if you will. The problem with the heating systems of the past is it was a design based on a top-down methodology, which said you produce all the heat that you need in that whole facility, no matter what the temperature demand is, at the highest temperature that's demanded. So high-pressure steam. And then you valve and heat transfer down to the lower temperatures. Ultimately, you have to redesign heating systems if you're going to get to the optimal efficiency solution, so that you take more of a bottom-up methodology, which that bottom-up methodology takes the highest temperature cooling to the lowest temperature heating, matches those up if the capacities match or close, and then go incrementally from there to design those systems to ultimately limit the work, the electrical energy that you have to do to supply to electrify those heating systems. This is a good example of that, because it's a literal project that we're working on right now that's applying based on the heating coming from an aquathermal energy storage system that's boosted to the underfloor heating temperature, and then you take that and only boost what's required for the domestic hot water and for the dedicated outdoor air ventilation that's going into that same building. So you only boost to what's required, and at the same time with that same heat pump, you're also producing the cooling temperature to get rid of the latent energy in those same air handlers, those same dedicated outdoor air handlers. But again, everything's hydronic. There's no DX in here, so it's all integrated in together. So then we can recover all the heat from the cooling that we're supplying to these same multifamily facilities to store in that aquathermal energy storage system to utilize later to increase the efficiency of the heat pump that's boosting it up to supply that heat. And I'll end there. And I won't even read these because I know I'm over on time. You can see them yourselves. Thank you.